Nearly 90% of large enterprises use artificial intelligence today. But across the corporate world, the terms AI and machine learning are treated as synonyms, jammed together in pitch decks and budget requests. Treating these distinct tools as identical leads directly to mismatched technological deployments. Imagine a company purchasing a massive, hardware-intensive deep learning architecture, only to assign it a simple task like calculating state tax variations. It is the equivalent of buying a commercial jet engine to power a golf cart. Understanding the technical boundaries of these terms dictates the reality of your project costs, your system scalability, and the operational risk you expose your business to. Failing to separate the overarching macro system of AI from its highly specialized subfields guarantees wasted budget on opaque, oversized systems that your team doesn't actually need. Artificial intelligence is the broad macro system containing technologies that mimic human cognition. Machine learning, a specialized subset inside AI, trains algorithms to detect patterns in data, improving automatically. Deep learning is an even more specialized subfield, nested completely inside machine learning. What separates deep learning from standard machine learning is its architecture. It relies on complex, multi-layered artificial neural networks designed to process vast amounts of unstructured information. All deep learning is machine learning, and all machine learning is AI. The reverse is never true. Mapping out this hierarchy is the mandatory first step to buying the correct tool. The historical baseline for artificial intelligence is the rule-based system. This relies entirely on human developers writing explicit, rigorous instructions. It requires absolutely zero historical data to deploy. Instead, it operates entirely on deterministic if-then logic. Take an early email spam filter. A developer hard codes a rule. If an email contains the exact phrase "win money," flag it as malicious. The trade-off is immediate. If a spammer swaps the letters for numbers and writes W1M 0 money, the system fails instantly. A human developer must manually rewrite the codebase to account for the new variation. Rule-based AI gives you perfect transparency and exact control over every decision, but it scales poorly and becomes highly fragile in environments that are constantly evolving. Classical machine learning abandons those strict hard-coded rules. Instead, you feed the system historical data and let it derive the rules itself. To function effectively, these models need roughly 50 to 100 structured data points per feature, alongside a human who curates those features so the machine knows what to look for. This matrix shows how the logic mechanism shifts. The machine learning model takes data, autonomously adjusts internal statistical weights, and identifies patterns a human would miss. This is ideal for forecasting housing prices or retail demand. The model adapts continuously as it ingests new data, but the output changes completely. You are no longer getting deterministic, exact answers. You are getting probabilistic outputs attached to a confidence score. Despite that adaptability, classical machine learning computations are mathematically lightweight. You can run these models on standard CPUs or small server clusters without breaking your IT budget. Classical machine learning serves as the true enterprise workhorse. You sacrifice absolute logical certainty in exchange for dynamic, highly scalable adaptability. When you deal with highly unstructured data, raw images, video files, and natural language, you have to scale up to deep learning and generative AI. The input requirements here are extreme. You need millions of raw data points and massive capital investments in specialized hardware, specifically large clusters of GPUs or TPUs. You also need time. Deep learning models do not learn instantly. They require intense computational training phases that often stretch from several hours to multiple weeks. This level of investment enables performance that classical models simply cannot reach, like human-level computer vision or synthesizing new blocks of text and functional software code. Deep learning delivers powerful results, but it demands an immense, often prohibitive capital footprint to operate successfully. There is a hidden cost to scaling deep neural networks up to millions of parameters. System transparency plummets. This is known as the black box problem. Consider the clever Hans effect in medical imaging. During recent trials, an AI model appeared highly accurate at detecting lung pathology from X-rays. In reality, the model ignored the lungs entirely, predicting positive cases based solely on physical pen annotations left by human radiologists. Because tracing the exact mathematical path of a deep learning decision through millions of nodes is nearly impossible, auditing these outputs for structural bias or fatal errors is incredibly difficult. The sheer complexity of deep learning introduces severe compliance, accountability, and safety risks, especially in highly regulated sectors like healthcare and finance. Success ultimately relies on matching the architecture to the exact data constraints of your problem, rather than chasing industry buzzwords. This decision tree flowchart outlines the process. The first routing question for any project is simple. Do the underlying rules of the problem change over time? If the rules are static, tasks like payroll, tax calculation, and basic compliance belong firmly with rule-based AI. If the rules do change, you ask the second question. Is your available historical data structured or unstructured? Structured historical data tasks, like retail demand forecasting and network fraud detection, route to classical machine learning. Unstructured data tasks, like building computer vision systems or natural language processing, route to deep learning. Accurately mapping your business problem through this logic tree prevents the fatal, expensive error of deploying an opaque deep learning model for a simple logic task. In reality, modern mission-critical enterprise applications are rarely built on a single pure AI methodology. Most rely on a hybrid approach. This method deploys machine learning to handle predictive pattern recognition, while simultaneously using rule-based logic to enforce safety guardrails. The trade-off is that this vastly increases your architectural complexity, but it is the only way to ensure both high predictive accuracy and strict regulatory compliance. Balancing interpretability and control against adaptability and scale is what allows an organization to extract actual return on investment from artificial intelligence.